Okay, so we're in chapter 7 now, and we're going to talk about bonding and a few other things. But in section 7.1, we're going to talk about ionic bonding. Okay, so recall that many main group atoms form ions that have the same number of. Just a second, let me get my marker here. That have the same number of ions or electrons as the nearest noble gas. For example, fluorine, its nearest noble gas is neon, and it is going to form, it's going to take on an electron, right? Because neon has more electrons. So it's going to form fluoride, okay? Sodium, its nearest noble gas is also neon, right? And sodium has one more electron than neon. So it's going to lose one to get the same electronic configuration as neon. Bromine is closest to krypton. It's going to take on one electron, so it can look like krypton. Potassium, can't see that number, it's too small. I guess it's 19, is closest to argon, right? So it's going to lose. How do you spell potassium? Okay. It's going to lose an electron, right? So this ends up, there's a sort of obvious consequence that comes from this. These elements have a tendency to take on a plus one charge. These elements have a tendency to take on a plus 2 charge. These elements have a tendency to take on a -1 charge, -2, -3, right? And so on, and 0, right? Because these are already noble gases. Now, main group atoms form ions that are isoelectronic with the nearest noble gas. Isoelectronic means that the group of ions or atoms that have iso... I'm really sorry, my vocabulary, it's the end of a long day, and I'm just struggling with this. Isoelectronic, it refers to groups of ions or atoms that have identical electronic configurations, okay? Isoelectronic means they have the same electronic configuration. Got to straighten my whiteboard out. All right, so after this happens, then these ions come together and make what is called an ionic bond. It's not really a bond, right? Sodium chloride becomes sodium chloride, right? Well, it's not really a bond because when these guys come together, there's a bunch of sodium atoms and a bunch of sodium ions and chloride ions, and they're actually come together in a 3-dimensional array. I'm only drawing 2 dimensions here, right? But it's not really a bond. It's really not an electrostatic interaction, but we do call it an ionic bond. All right, so the stability of noble gases are a result of their electronic configuration. So a filled valence shell results in high stability. A filled valence shell results in high stability, okay? Main group elements either lose, gain, or share electrons in order to have a filled valence shell. In ionic bonding, they lose or gain, right? And that makes the element isoelectronic with a noble gas. All right? So for all main group elements, the number of valence electrons is equal to the last digit of the group number. So in our lab, we've got a periodic table. Let me go back up to the periodic table here. In our lab, we've got a periodic table. Let me show a bigger one than this. So in our lab, we've got a periodic table which has groups 13, 14, 15, right? It doesn't have these other names down here. So in our lab, I'm pointing at stuff here. Can you see this here? I don't use this marker very often, so hopefully this will work out nicely. No, that's not what I want. All right. Nope, that's not what I want. No, that's not what I want. All right, beg pardon, folks, here. Give me a second here. All right, let's just come back here and go back here to, all right. So group 14 is here. So what the author of this text is saying, the last digit of this group is 4, right? Well, some periodic tables call it group 4, right? There's 3 ways to name these periodic tables. This one has all 3 of them, 4A, Roman numeral 4A, right? Roman numeral 4A, and 14. So that's what this statement here means. Let's go back here. For all main group elements, the number of valence electrons is equal to the last digit of the group number, right? So carbon is 4, nitrogen's 5, oxygen's 6, and so on. because in that one nomenclature system, the group oxygen is in is called 16, right? But others call it 6, so it's fine. It's the same thing. Main group metals form cations by losing all of their valence electrons. Main group metals form cations by losing all of their valence electrons, resulting in a filled valence shell. So calcium, its electronic configuration ends with, I don't remember, is it 4s2? Okay, is that right? 1, 2, 3, 4. That's right. Its electronic configuration ends with 4s2, right? So I think it's argon, 4s2. These all get lost, resulting in a filled valence shell that looks like argon. So it becomes calcium 2+, right? This is exactly what you would expect. So just want to point that out. I know it's probably obvious when I point it out. Transition metals and intertransition metals behave differently than main group metals, and we're not really going to get into that. We talked a little bit about it in a previous conversation, but I don't want to say much more about it now. The cations formed by transition metals and intertransition metals are typically not isoelectronic with a noble gas, and we have to be told what those are. We look those up in a book, or we're told by the name, or we're told by looking in a table or something like that, right? So the cations formed by transition metals and intertransition metals are typically not isoelectronic with noble gases. They're not really predictable. Anions usually form when a nonmetal atom gains enough electrons to have a filled valence shell. So oxygen, periodic table looks like this: oxygen, fluorine, neon, right? Nitrogen. Oxygen wants to become like neon, right? Because it's the closest noble gas. So it's going to pick up 2 electrons. So oxygen is going to go to oxygen 2-. The charge of the anion is equal to the number of electrons gained by the atom, of course. All right, so I think that's all I want to talk about with respect to ionic bonds. I think this is pretty intuitive. Of course, we're really going to learn it when we practice it with our homework problems.